So you can actually cause the phase behavior of a material to change by changing a pressure. Now, what is pressure? So pressure, of course, is the effect of the gas that is around us that is squeezing on ourselves all the time. So we get so used to it we don't even feel it, but actually the pressure of the air around us is pretty high. It's called 1 atmosphere of pressure, and it's essentially a force that's squeezing on us all the time, that our bodies are squeezing out at. Now, you know from either experience or not that if you climb a very high mountain, the amount of air that is around you decreases. So let me show you what the phase behavior of water looks like as a function of pressure. So here's the phase diagram that I showed you before. At 0 degrees Celsius, water transitions from a liquid to a solid, and at 100 degrees Celsius, water transitions from a liquid to a gas. If we increase the pressure to about 1.5 atmospheres, then it turns out that the solid-liquid transition still occurs at around 0 degrees Celsius. It doesn't change very much, but the liquid-gas transition occurs at a higher temperature. It's at about 112 degrees Celsius. Whereas in turn, if we lower the pressure, so if we went down to about, say, 3/4 of an atmosphere, then again the liquid-solid temperature stays about the same, but the liquid-gas transition temperature decreases to about 92 degrees Celsius. Scientists like to organize this in what we call a two-dimensional phase diagram. So this is a phase diagram where on the x-axis we have the temperature, and on the y-axis we have the pressure. And what we do is we label the locus of points where the material changes from a solid to a liquid to a gas by simply connecting the dots of the lines that we've just drawn before. And this is something that we call a phase diagram. So this is a two-dimensional phase diagram, and you see in this phase diagram that there is a region, there's a big region where the material is a solid, there's another region where the material is a liquid, and there's a third region where the material is a gas. At any point that you are on the phase diagram, so you can always find out what the behavior of the material is. So, at 1 atmosphere and about 23 degrees Celsius, you can read off this plot that water is a liquid. But this allows you to generalize it to many other conditions. And so nitrogen has a phase diagram that you'll see looks a lot like that of water, and there's a solid phase, a liquid phase, and a gas phase. At low enough pressures, actually, nitrogen also has a situation where the solid phase transitions directly to a gas without a liquid phase, but there's this big liquid phase, which is the part at 1 atmosphere that gives rise to liquid nitrogen.
If we change the pressure, we can change the phase of the liquid nitrogen by cooling it. I'm going to use this vacuum system, and as it evaporates, the heat goes off with the gas, and the liquid that's left behind gets colder and colder. And at some point, we're going to get below the melting temperature of nitrogen, and hopefully we will see solid nitrogen. And I'm going to do this. First, I'm going to turn on the pump, and then quickly. So the nitrogen is boiling now because the pressure over it is lower than its vapor pressure. It's internal heat that's causing it to boil. It boils, it cools, and then what we see is solid nitrogen. Here is dry ice. If we raise the pressure, we can put the dry ice, we can put the carbon dioxide in a place where it can exist as a liquid. Going to seal it up so that the gas cannot escape. Because the gas can't escape, the pressure inside of the tube is going to go up. When the pressure inside of the tube reaches about 5 atmospheres, the dry ice reaches a point where instead of going directly to gas, subliming, it can melt. It can turn from a solid to a liquid. Now what's going on right now is heat going into the tube is causing the dry ice to sublime. As the gas builds up inside of the tube, the pressure goes up. And as the pressure goes up, there it goes, the dry ice now can melt. Now we have mostly liquid. And if I release the pressure, the the liquid carbon dioxide can no longer exist as a liquid. And because it's still cold, it condenses straight back into a solid.